But I think what can be hard about number 24 is it follows 21. And what I mean by that is in number 24, they tell you that the two people, and there's a mother and a daughter who are ice skating. And they say that they don't say anything about the friction between the skates and the ice for either the mother or the daughter. But the fact that they say ice is what I wanted to point out. If they say ice, they really want you to say that the friction is 0 or some small number if they give you some information about that friction. And that's why it's confusing, because 21 is also on ice, and they give you some information, and you'll see that they do want you to consider the friction, although it is very small. But then in 24, they don't give you anything about the friction, and so that's kind of the clue that they want you to say it is so small that we can just treat it as 0 or close to 0. And so in our equations, we'll just call it 0. And that's, again, why I think 21 and 24 confuse students. So let me start with number 21. And so coming over here, chapter 3, number 21. 21 says this. It says, if a pole is 210 that accelerates a 40 kilogram child on ice skates at a rate of 5 meters per second, what is the frictional force acting on the skates? Okay, so I'm going to start with what we call the free body diagram. It's really very helpful. And so if I have this child here, and I'll just make a little stick figure, and it says that there is a pole of 210 newtons, and so I'll just make something up in my head. Maybe there's a rope, and I'll be the dad, and that's the child, and I toss the rope and say, okay, grab that end of the rope, let's go, pull, and I pull the child. So I'm pulling the child with this force of 210, and then what they're saying here is that there is some friction, some rubbing between the skates and the ice. Now it is ice, so I know this. If it's not 0, it's something really small, and that's what I'm trying to point out in here. But see, they give me information. They even ask what it is. So I'm going to leave it as a variable. I'm going to know it's ice. I'm going to know it's going to come out small, but I'm not going to treat it as 0. And in 24, they don't say anything, so I am going to treat it as 0. And I think that's kind of the confusion between 21 and 24. All right. But I do want to point out this one because this problem has 2 steps. And I think any problem that has 2 steps is why it gets that little triangle, because students want to just stop after one step. I'll point out that they said the child accelerates at a rate of 5 meters per second each second. And so step number 1 is to apply Newton's second law, which says that the net force is equal to mass times acceleration. And, I didn't put it on the board, but they did give the child's mass too, 40 kilograms here. So let me put that here. And let me just check to make sure I didn't leave anything off here. But let's see, 40, acceleration, 210, okay. So in this case, I would say, okay, the child's mass is 40 kilograms, okay, good. The acceleration is 5 meters per second squared. And if I take 40 times 5, I get 200. And a kilogram meter per second squared was our definition of a Newton. And so the net force is 200. And let me give this warning again. Don't stop there. You heard me say that in the lecture here on chapter 3. A lot of students do stop right there. And when I'm grading the test, I go, okay, well, they did half the problem. And you'll see in each problem I graded on 3 points. And so I go, okay, well, there's 1.5 points. Because they did the first step right? They did Newton's second law. But what they're leaving out is the second step. The second step here, then, is to remember that net force is not the frictional force. It is also not the force from Dad pulling. The net force is the combination of all the forces put together. So if they're asking for an individual force, you got to keep going. Now, if this would be an easy problem and probably wouldn't have a triangle if it had said, hey, find the net force on the child. Well, yeah, net force is easy. It's just mass times acceleration. But you have to go one more step, because then you have to say this. You have to say, all right, and I'll get out of this thing's way. You have to say net force is equal to the force the dad is pulling minus the friction. And of course, that's where our arrowheads came into play. And so if you remember us having that discussion on vectors, when we combine them together, sometimes we add, sometimes we subtract, and sometimes we do Pythagorean's theorem. It all depends on what direction they are. And so that's where the free body diagram really helps. And so this free body diagram is showing that I've got this one to the right and this one to the left. Okay, so that's why I put the subtraction up here. All right, so then knowing that this is 200, because I just worked it out, and this is the 210, I can then move the frictional force over to here, and I can then move the net force over to here, and I get the answer of 10 newtons, okay? So that's this idea. And so those of you who may not have asked any questions, hopefully you didn't stop right here, but I'm guessing that there might be 1 or 2 of you out there who did stop there. And hopefully I'm correcting that now. So you'll never do that again, and particularly Monday on the test. You'll say, okay, wait. Remember, Newton's second law doesn't give you the frictional force. It does not give you an individual force. What it gives you is the net force. And so if they're asking for one individual force, you're only halfway there when you do this step, okay? All right, so this one does have some friction. By the way, notice it's a small number. And that's really what happens when you put something on ice. There is very little rubbing and very little friction. So that's why I was saying number 21 can be confusing with number 24, because number 24, they don't say anything about the ice and the skate interaction. And because they don't say anything, I'm going to assume that they are letting me come up with the conclusion that the friction is negligible. It's so small I can treat it in my equations as a 0. And again, that's why 21 can be, and 24 following 21 can be confusing, because right here we just saw that there is some friction. But I want to point out it's a small number. Because watch this one. In this one it says you have a mother who has a mass of 50 kilograms and a daughter who has a mass of 25 kilograms, and they are ice skating. And it looks like they get on the ice and they kind of face each other, and then the mother and the daughter push off each other. And so it maybe looks something like this. I'll be the mother here, and here's the daughter, and you go push. And this is then Newton's third law problem. And so if the big stick figure will be mother and little stick figure will be daughter, when they push, then mom is pushing on daughter. There's F. But notice there's 2 objects in here. So then daughter is also pushing on mother with a force that is equal and opposite. And so that was our Newton's third law. And so this one is a third law. But it's also a second law too. And you'll see that in just a second here. Because the second law says this. It says, okay, so if you want to know the acceleration of mother, so I'll put an M, you need to get the net force on mother and divide by the mass of mother. But to find the acceleration of daughter, and so I'll put acceleration of daughter, you need to get the net force on daughter and divide by mass of daughter. And this is where the third and the second law can really give students a hard time. So again, notice the third law is saying the forces are equal and opposite, but notice they're also saying they're on different objects. So when I go to do a calculation, this net force on mother involves only the forces on mother. And so I'm going to then put a blue line around what I'll call the free body diagram of mother. And I will put a green line around what I'll call the free body diagram of the daughter. And notice that these forces are on different objects. And so when you go to add them together, you would not add this force together with that force because they're not on the same object. You just want to know what the acceleration of mother is, so you put the forces of mother. And you want to know just the acceleration of the daughter, then you have the forces just on the daughter. And so be really, really careful here. In other words, what we're doing here is we are applying Newton's second law twice. We're applying it once to mother and once to daughter. But the third law, right, is saying that the forces from between those two are equal and opposite. And the reason that's important here, and let me put some more numbers up here, they say the mother has a mass here of 50 kilograms, okay, and the daughter has a mass of 25 kilograms. And here's the real key. It says here, they faced each other and the mother pushes on the daughter in such a way that the daughter accelerates at 2 meters per second. So if I come over to here, I can put in a 2 meters per second for the acceleration of the daughter. That is directly given. Now the mass of the daughter is 25. So I can now find the net force on the daughter. And so the net force on the daughter would be this 25 kilograms times the 2, and so that's 50 newtons. And I think that is almost the answer to the first question. The first question says, what is the force exerted by the mother on the daughter? Watch those prepositions. By mother, so by, and on daughter. Because what I have right now is 50, but this is the net force. And just like I said back here in number 21, be really careful. Net force doesn't give you the individual force. It gives you the combination of all the forces. And so here's where we have to kind of assume the author is saying here that then this 50 would be this force, and I'll just say, you know, from mother minus the friction, but if the friction is equal to 0, I can then really say that the net force is the force coming from the mother. Because remember, net force is the combination of all the forces. And if there's only one force, then net force and that force are one and the same. And so in this sense, that's an easier problem than 21. 21, the net force got me halfway there, and I had to continue on to find the individual force. Here, because there's only one force on the daughter, once I find the net force of 50, that is also that one force coming from mother. All right, so there's the answer to the first part of this question. So it's 50, and I'll just read it again. What is the force exerted by the mother on the daughter? And then it makes the next one pretty easy. What then is the force exerted by the daughter on the mother? So in this diagram, we just found that this here is 50. But as we already talked about, Newton's third law would say they're equal and opposite. So if mom puts a force of 50 on daughter, then daughter is putting a force of 50 on mother. They're equal and opposite. All right, so those are the first two questions. So both of those forces are 50. And then finally we can answer this last one. Then what is the acceleration of mother? And so if we come over here and do this calculation, and I'll say it again, we know the force on the mother from the daughter is 50. What we need is the net force. And the net force is the combination of all the forces. But again, if we just say that the friction is 0, then all the forces, there's only one force. And so that net force is the same as that one force. And so I will put here 50 newtons. And now the mass of mom is more than the daughter. And so notice in this calculation, both the mother and the daughter have the same amount of force on them of 50. But they don't have the same mass, which is why they don't have the same acceleration. And so in this case, I get a value of 1 meter per second squared. Excuse me, for the mother. All right, well, I hope I didn't take too much time, but like I said, looking ahead in these next couple chapters, they're not very long, and I thought that I would address some of the harder things that you guys seem to be asking, and it also was kind of my way of saying, look, I've never done this remotely, so I'm not really sure what's working for you and what's not working for you. And so I thought I would carve out a little bit of time and say, let's do that. And also, we're not really on a time schedule like we would in normal class, because I don't want this to take away from a review or a summary of Chapter 1, and it won't. It just means I may go over some time frame. All right, well, that took me a good while to do here. I'm looking here at the clock. Let me erase the board and then say, I hope that helps, at least some of you. And let's go ahead then and go back to our lecture on Chapter 4. If you remember, Chapter 4 was one that was trying to talk about what I'll call two-dimensional motion. Your author called it motion in a space. And so here's where we had gone. We said, okay, Chapter 4. Let's look at motion in space. And as I said last time, don't think of that as outer space. That's just two-dimensional motion. And I said there were kind of two flavors for this. There was this start of what we call a circular motion, and that was the lecture we already did. And I talked about centripetal acceleration and centrifugal, and how centrifugal is fake, but centripetal is the real one, and it's got a lot of little subtleties to it. Let me not repeat that lecture. But the second half of this chapter is projectile motion. And so let me pick up then and do the second half of this chapter with what we refer to as projectile motion. And what we mean by projectile motion is just simply this. Let's see if I can find a simple object. How about this tennis ball here? But projectile motion is just saying, what would happen if you launched something, and it doesn't matter how you launch it. So in my case, I'll just kind of toss it with my hand. But it could be fired with some gunpowder, so it could be like a cannon or a bullet. It could be fired with, a slingshot or some elastic band. All of that is not the discussion, how it got started. The projectile motion is once whatever got it started lets go, then what happens? So in other words, ignore this part for now. Ignore the part where I'm giving it an acceleration. And our thoughts will pick up right here when my hand lets go of it. So it would look like this. I toss it. And so as it goes across the room, you will see, I think, that it is moving both horizontally, x, and vertically, y. And so that's why we call it motion in space. It's a little more than what we have done. And so I like to say this: motion in both x and y. As you'll see here, we will call this motion, or we'll call the whole motion projectile motion. But when we look at one part of the motion, just the x motion, we'll say it's a component. And so I'll just put on the board here that say the components. That is the x and y motion. Act independently. And here's some good news. When you first stop and think about projectile motion, it looks like this is going to be something pretty hard. But as you will hopefully see here in a few moments, the components act separately. So, if you know how to do one-dimensional motion, and you do, that's what we've been doing in chapters 2, where we described motion, and then chapter 3, we explained the motion. When we get here in chapter 4, I hope what you will see is I will just apply that same strategy of chapters 2 and 3, first to the x motion, and then to the y motion, and I'll apply it separately. And so we like to say this: two-dimensional motion is actually easier than it looks. Two-dimensional motion is actually one-dimensional motion twice. So the good news is if you already have learned chapter 2 and 3, if you already know how to handle one-dimensional motion, if you already know how to do these problems that I was just going over, things like, hey, if you throw the ball upward and it goes up and down, and if you know how to solve that problem for one-dimensional motion, then you also know how to do two-dimensional motion, because you're going to do one-dimensional motion twice. Now, of course, that means the problems are harder, because everything you did in the last problems you have to do twice. But again, if you know how to do it the first time, presumably you know how to do it the second time. So I can't say this enough, that nature is kind of nice to us at this point. Nature has said that when something moves in two dimensions, there's not a new piece of physics. In other words, we don't have Newton's laws of motion that change when we have two-dimensional motion compared to one-dimensional motion. It's the same laws of motion. In fact, more than that, we don't even have to learn really anything new other than we just have to do the motion twice. Watch, I set up 3 fun experiments here that hopefully will come across on videotape as exciting, because usually when a face-to-face they're kind of nice. I'll start with the simplest one. The simplest one, I'll call it old school technology. It's very simple, it's very low tech, but I think, believe it or not, it illustrates it better than the other 2 high-tech ones I have. But I'm going to show them all to you. So watch this for a moment. Here is going to be my 2 objects. Okay, one is a solid sphere, and one is a sphere. It's a ball bearing that has a shaft drilled out through the middle. Watch, because this little apparatus has a little spring on it. And if I pull it back a little bit, or if I pull it back a lot, and so notice there's 2 settings I can pull it back to, and I put the one with a borehole on it over this shaft, and I let it go, you can kind of see what's going to happen. It just falls straight down. Because when I release it, the shaft slides out of the borehole and the metal ball bearing just falls straight down. I would call that one-dimensional motion. I would say that I'm hoping at this point you know how to handle that problem. This was like the one I just did about dropping the rock in the well. It starts with a speed of 0, and we could ask how fast and how far is it going after 1 second, 2 seconds, 3 seconds. Okay? So keep that in mind, because let me set it up again. So I'll move this back, and I'll just go to the low setting. I'll put this one on here that's going to drop straight down. And the second one, I'll put on this edge. And I'll take this one off for just a second so you can't watch it for a moment. But if I release this one, you'll see that the shaft comes along and just kind of kicks the ball sideways. Just gives it a little nudge and pushes it. And so this ball is what I will call projectile motion. How it got started doesn't really matter. But once it got that little kickstart, you can see that once it goes off, it is going sideways because of the original kick, but gravity is pulling it down. And the main point of this little experiment is to do them at the same time. And I'm hoping you will see this. Look carefully for this. Because when I release this first one here will drop straight down. It will only have one-dimensional motion. But this one over here will have a sideways motion, an X motion. But gravity will start to pull it down and give it a Y motion. And I want to convince you that even though this second one has a X motion, even though this second one has a horizontal motion, both of them will fall down at the same rate. They will hit the ground at the same time with the same vertical speed. And this is my way of saying that it doesn't matter that it has horizontal motion. The Y motion is still treated the same, whether it has some or doesn't have some. And so let's watch it. Again, this one, no X motion. This one does have X motion. But notice they will still have the same Y motion. The Y motion is not affected by the X motion. They act independently. That's why I was saying, when we go to do our calculations here in a moment, we will treat them separately. Okay, so here we go. Count of 3. 1, 2, 3, release. Yay! And like I said, kind of low tech, but I hope you see it. Let me show you a second time, because remember I showed you that this little apparatus I could put back on a bigger notch. And if I pull the shaft back a little bit further and I do the same thing, hopefully again you'll see the same thing. I'm going to release it, and this time, this first one again will have no X motion. This one will now have more X motion. But my point is this. My point is it doesn't matter whether it has a little X motion, no X motion, or a lot of X motion. They all act independently. And so watch the vertical drop. The vertical drop of these will be exactly the same. They will be falling down. They will be the same height all the way down. They will take exactly the same time to hit the ground. Okay. The only difference is, I should point out, is this one's going to go straight down, and this one's going to have a X motion, but they're going to be something like this. Okay, 1, 2, 3, go. Yep, and sure enough, they hit at exactly the same time. Well, like I said, I'll show you 3 of these, but all 3 of these are hopefully going to just keep illustrating the same thing, because when we go to do some calculations here, I'm hoping that it will make sense to you why, when I do my calculations, I will think of just X by itself. I won't worry about Y. And then I'll do Y, and I'll think of Y by itself without worrying about X, to figure out where in the world is this object. Well, I'll go to a little fancier one. We call this the high-tech one. And sadly, the high-tech one is not that accurate. But I like it, and hopefully you'll like it. I'll give it a try. I'll turn it on first. It does have a cannon inside. Let me reach inside this little bucket here and hold it up. Here's this little cannonball. And inside, I can push down. That loads the cannon. And on this side by me, there's a little infrared beam. There's a notch on top and a notch on the bottom. You can't see it from your side of the room. But I'll just use this little card here to break the beam. And see, when I break the beam, it fires the cannon. Watch, I'll show you again. So load the cannon. This little card, I'll just swipe in front of the beam. Ah, see, there's why I say it's not very good at repeating itself, even though it's this high-tech thing. All right, so maybe I'll just fire it a third time, but what I really hope is that it is adjusted to go straight up and straight down. And so straight up and straight down. But watch this now. On this track, there is this little post, because when this goes by, it will break, whoa, didn't break the beam and fire the cannonball. Where does it land? And so if I give it a little nudge and it fires up, it lands inside. Why does it land inside? Well, there it is, a little off. And that's because the horizontal and the vertical motions are separate. And so if the cart has a horizontal motion, so what? That means the ball also has a horizontal motion when it's fired. And the cannon just gives it a vertical motion. Maybe I'll do a little adjustment on it. But the cannon gives it a vertical motion. Gravity also gives it a vertical motion. So the cannon starts pushing it up. Gravity pulls it back down. And all of that vertical motion is independent of the horizontal. And so it keeps its same horizontal, and so does the cart. So it just goes up and straight back down. And so this is hopefully an illustration that the X and the Y are independent. Well, one more. Why don't we try another one? And again, I'll keep my fingers crossed on this. It works most of the time. But it's a real fun one. You might have been wondering why these posts were blocking our view earlier, and I didn't want to mess with them because I had them all set up. But this is a little blowgun. This little metal piece will be my bullet. And in a moment, I will put the bullets in the blowgun, and then I will blow on the end, and I got a little rubber connection here, and I'll kind of blow on here and go. And when I blow on the end, it will shoot this bullet. Now over here, this tall post is going to be this metal can. This metal can will stay up because of a little electromagnet. And so I'll put my metal can up here. But you might be noticing that there are wires that go from that electromagnet. Oops. Hard for me to tell from where I am if it's centered or not. Okay. Let me stand back. Oh, okay, I think that's good. But over here, for my blowgun, and the reason I didn't want to put the bullet in there quite yet, is if I look through the center of my blowgun, it should be pointing right at the can. And good, it still is. I had set it up before we started filming here today, and I was afraid I might bump it or something, but it still looks good. And so I'm still pointing at the can. And so what's going to happen is when I blow, it's going to come out of here, but then once it leaves, that's when it becomes a projectile. And as a projectile, it's going to begin to fall. See, if there was no gravity, Newton's first law would say it's in motion, it's going to continue, and it would just go in a straight line. And the reason I'm pointing at it is because a straight line would hit it. Now, this whole mechanism here at the end of my blowgun is a little switch that when this leaves the end of the blowgun, it turns off that magnet. And when it turns off that magnet, that metal can begins to fall. Now, I'll say it again, if there was no gravity, so if we were doing this in outer space, what would happen would be this, is we would get to the end, the switch, of course, would turn off the magnet, but if there's no gravity, that's really kind of irrelevant. The can would stay there. And again, if there's no gravity, the bullet would go in a straight line, and the bullet would hit the can. But of course, we're not in outer space. There is gravity. And so when this bullet exits and turns off this electromagnet, that can is going to fall. But so is this bullet. And that's the whole point of this demonstration. They fall at the same rate. And so, as the can falls, the bullet falls, and they fall the same amount. So where the bullet would have gone, which was right here without gravity, it would fall the same amount. And that's a nice way of saying the can, which has no horizontal motion, will fall the same amount that the bullet falls, even though it has horizontal motion. And that's my point. See how they act independently of each other? And they will be at the same place, and they should then hit in midair. And so what's really nice about it is, in theory, and it usually works, so I'm keeping my fingers crossed, but 9 times out of 10, it hits beautifully in midair and is a great illustration of how it works. Okay, so let me just show you, now that I've explained the physics to it, and so I'm pointing at the